Okay, so first problem, you are given a vector, and there was a confusion because I called the number of columns to be R, but it doesn't really matter. So on your midterms, it's written as the letter R, but you should be able to solve the problem regardless of what that letter is, okay? Um, so this is a row vector with any number of elements, and you are asked to keep the even ordered elements. That means you want to keep the second, fourth, sixth, and so on. So this is not asking you to keep the even numbers in the vector. You are just looking at their order. All right. So in one of the homeworks, you are looking at dividing each number by 2 and checking whether it's an odd or even number. So that's not the case here. So what you do is you need to generate a vector by which you can index this vector A. So if you were to write it long-handedly, you would say you want 2, 4, 6, 8, and so on. Okay, but you want this vector to work regardless of what the size of A is. So you need to be able to generate this set of numbers from the size of A. So if A goes all the way up to 10 elements, this needs to stop at 10. Right? So if you look at this, you can just generate it by saying 2 colon 2 colon all the way to number of elements in A, or you can, instead of saying number of elements here, you can also say C, or if that's in parentheses, you can also say E and D. That's the first A2 colon 2 colon E and D. That's how you refer to the even ordered element. But what do you do with them? You have to remove these elements from A. And the way to remove elements from a vector or a matrix is by saying equals empty vector, right? This is a special meaning when you set, when you index a matrix and set it to be an empty vector, you are removing those elements from the vector or matrix. Okay? Another solution to this problem is to select all the other elements of A and then save those back into A. So this is the first solution. The other solution is to say A equals A, select 1 colon 2 colon E and D. But this expansion is saying 1, 3, 5, 7, and so on. So you are indexing A, referring to all the odd ranked elements, and selecting them, pulling that into A. So now A becomes this new vector where the numbers are selected from the original A, and you're only keeping the even ordered element. Okay. Any questions? Second problem. You are asked to write what this expression will generate, what numbers each expression will result in. You start from 3, okay, so you have 3. And then you have a step size of 3, and you go all the way to, once you go all the way up until you reach 3. Okay, so you're already there. That's where you stop. So the first number is 3. So this expression will generate number 3. The second expression, you start from 7. You go up 3 by 3. You'll never reach 3. So that gives an empty vector. So this does not contribute any numbers to your overall vector. The third expression, you start from 8. You go by minus 3 until you reach 3. So you'll get 8, 5, 3. Next number is going to be 1. You are already below 3, so that's not going to be included. So this expression will contribute 8, 5, 3. Okay. And the last expression includes a reshape and rep math function. RepMat takes a matrix and replicates it. So you have 1 and 2. That's going to be the block that you're going to replicate. You replicate it twice along the rows. You'll make another copy on the row. And you replicate that along the column twice. So you end up with 2 each along the column. And each of these small blocks is going to contain 1, 2, 1, 2, 1, 2. Okay? Eight, yes, yes. 8, 5, and then the next number is 2. So 3 is not included, you're right. All right. So thanks for correcting. Okay, so and then you take this matrix and you reshape it to be 1 row, and you want MATLAB to automatically adjust the number of columns for you. So we'll take this and make a 1-row vector. And when you reshape a matrix, the linear order doesn't change. So the original matrix and the reshaped matrix, if you go column by column, you should hit the same numbers in the same order. So we'll take this, we'll go in the column order like this, and then we'll write down the numbers we have. 1, 1, 2, 2, 1, 1, 2, 2. The answer to this problem. Okay. All right. Next problem is about strings and variable scopes. And here you need to understand that even though this function has a variables named A and B, they have nothing to do with the variables A and B in the command window. And things only get to be related to each other as soon as you pass variables or values. They get to be copied to the function variable. So if it makes it easier for you, what you could do is replace all of these A's with X and replace all the B's with Y. That's what I'll do. And I'll keep solving the problem like that. A equals apple. We have a variable A that contains the vector apple. It's a character array that contains these 5 letters. Next, we pass A. We pass this value into the apple function. There's also a function called apple. And this value will be copied into X. So as soon as you call the function, you are creating a variable named X that contains the string apple. All right? Next, we add 2 to it, 2 to X, and convert it into a character and store it in Y. So what this will do is it will create another variable named Y, where each of these characters is added by 2. So you add 2, you get to C, PQR, PQR, LMN, EFG. So Y will contain C, R, R, and G. Next, you are adding 2 to X and then storing it back in X. That will make this C, R, R, and G. But you're really not using this new value of X for anything, so you don't even have to do this calculation. So as far as solving this problem is concerned, you can actually ignore this line of code because it has no consequence. So you don't have to say characters so you're right. When you do X plus 2, this will actually not be CRRNG. It will be a double vector that has the numbers corresponding to each of these letters. Okay, whatever 97. So this will be 99. Right? But you really don't care what those values are, and you really don't care what the new value of X is because you're not really using it. The value of Y is the one that's being returned from the function. That's the one that you care about. So this value is returned from the function and is stored in the variable b back in the command window. So b will now contain c, r, r, and g. So that line is done. Now in the next line, we call the apple function with a new value orange. So the orange is a vector. It's not stored in any variable. It's just created on the fly and it's passed on to the apple function. Okay. But you really don't need to see what the result is going to be for this function call because we are not really storing it anywhere. So you are calling a function just like saying square root of 5, semicolon. If you don't have, let's say, a equals that, then you don't really need to know what square root of 5 is. You don't need to do any calculations. You can ignore that line as far as the a and b variables are concerned. So if you want, you can follow this for this x equals orange, and then add 2 to it, store into y. So y will become r, oh sorry, q, p, and so on. And then y is returned, but it's not really stored in anything, so you can just ignore this. All right, so this line doesn't change the values of a and b in the command window. Right, you are calling a function, it still executes, but it has no consequence as far as the answer to this problem. Okay, and then in the last line, you concatenate a and b. That means you have two vectors, you put them together, make them one longer vector. So that will now be one long vector that contains apple and R, and G. There are no spaces, and MATLAB will print it, and then the answer is going to be apple, P, R, and G. Okay? All right. Next problem is about converting a linear index to row and column indices for a matrix size 1,000 rows and 10 columns. So this is M. The last element in the first column will have an index of 1,000. Okay. The last element in the second column will have an index of 2,000. This one will start from 2001, 2002. You are going all the way to 2,468. And you are trying to identify the row and column indices of this element right here. The row index is just going to be 1, 2, 3, 4, 5, all the way to 468. So x is equal to 468. And the column index is 1, 2, 3. All right? Make sense? Questions? Comments? Okay. Moving on. We are given a matrix with 2 rows. And we want to remove columns from A, columns from M, such that any column where the second row is a square of the one in the first row are removed, and also any column where the first row is greater than the second row is also removed. So let's do this in multiple steps first, and then we'll show you other options that you have. So we could say M first row all columns. Let me rewrite this. First one comma colon. So this will give you a row vector containing the first row. If M is like this expression M1 comma colon will just give you the first row. And we are comparing that with the second row, M2 comma colon. Right, so I have two separate vectors now, the top row and the bottom row, first row, second row. And whenever it's graded, I'm going to remove those entries. So this expression, one vector greater than the other vector, is going to produce a logical vector of zeros and ones. Wherever this condition is satisfied, you will have a true element in that vector. And wherever it's not satisfied, you will have a false for that location. So you will get, as a result of that comparison, a new vector. You'll have zeros and ones. And wherever the first row is greater than the second row, you'll have a 1. And those are the ones that we are trying to remove. So we'll take this index, this logical vector, and use it to index M. Okay? But we want to use it as a column index. So we need to say both rows, comma, whatever this logical vector is. So M, colon, comma, that expression. And those are the ones we are trying to remove. We're going to say equals empty vector. All right, so this statement will remove any columns of M where the first row is greater than the second row. All right, and you can set up the next condition similarly. M colon comma where the second row is a square of the first row. So M first row dot square equals M second row. Again, you are taking this second row, and you are comparing element by element, and you are generating a logical vector by saying equal. Wherever there's a 1, this element in the second row is a square of the first row. All right? And then you will remove those elements also. Equals empty vector. Okay? Now you can combine these two statements into a single longer statement. I want to be lazy and I'm not going to show you the full expression, but I'm just going to, I don't know how to use the erase on this. So you don't have that, and then you'll put an or expression right here. You don't have that. Okay. So you're saying colon, comma, and you have an expression that generates a logical vector. You have this logical vector, which is a greater than sign comparison, and then you are saying or. So whenever that is satisfied or whenever this is satisfied, that will give you a combined logical vector. And it's good practice to put these in parentheses so you don't have to worry about the order of operations. So you had one logical vector for comparison of greater than, and a second logical vector for square, and then you are ORing these two together. And wherever there's a 1 in any of them, the resulting vector will have a 1. So effectively, you will be removing any column that satisfy either of these conditions. Okay? All right, so this is one way of doing it. And I'll call this large expression right here. I'll call this the I equals. So you can separate this into two lines. First, you would say I equals that. And then in the second line, you would say M colon comma I equals that. Similar to the first problem, the opposite of this is to generate a new matrix with the things that you want. So this is where this solution removes the columns that you don't need. In the other solution, you would say M equals M colon comma not We are selecting from M all columns, all rows, and those columns that don't have the first row greater than the second row, and it doesn't have the first row being a square root of the second row. And you keep those, you select those and you store it back in M. All right. So both of them will do the same job. You either remove the things that you don't need or you select the things that you need and store it back in M. Any questions? Okay. Question number 6 is about for loop. I'm just going to rewrite this, make it easier for me. Okay. And let me rewrite M also. So I have this matrix right here. So M is a 3 by 3 matrix. Size MF M1, that means you are looking at the first dimension, that's the number of rows in M. So this expression will be 3. So the values of A go from 1 all the way to 3. So this expression right here, this expression generates a vector that has 1, 2, 3. So those are the numbers that A will go through as it iterates over the for. And the first value of A is going to be 1. So we'll draw a box A, it has 1 in it. Okay. Next we go into the for loop. The values of B are going to go through 1 all the way to A. So that's going to be 1 all the way to 1 as a single element 1. So those are the values that A will take for this iteration. So B will be 1. Let's draw a box, B 1. So what do we do with these A and B variables? We use them to index M. So we'll take M11, all right? And that's the first row, first column is the number 5. And we take it, we store it at the end of X. X is initially an empty vector. After we expand it by 1, X will now contain 5. Okay. All right, so the for loop is done. There are no other values of B to go through. So we're going to move on. That's the end of the first iteration of the A loop. We're going to move on to the second value of A. Now A has 2. And B will go through values of 1 all the way to 2. So these are the values that B will go through, 1 and 2. For each one, what we do is we take MAB, so that's M21, second row, first column, that's number 3, we add it to the end of X. And B loop is done. The iteration of B is done for B equals 1. Next, we do it for B equals 2. That'll give us M22. Second row, second column, that's number 4. Okay. We'll move on to the next iteration of the A loop with A equals 3. And then B will take 1, 2, 3. Those are the values that B will go through. First this expression will run for M31, and then it will run for M32, and then it will run for M33, where B equals 1, B equals 2, B equals 3. Okay? So that's the third row, first column, number 2. Third row, second column, number 6. third row, first column, number one. So the answer to this problem is 5, 3, 4, 2, 6. All right. Make sense? Okay. Now let's move on to the programming problem. You can solve this problem with for loops or without for loops. And I'll show you a solution that uses just matrix operations instead of for loops. Okay, so we have the matrix M. If I can that one, let's try this again. I can do it nice. So M will have any number of rows and any number of columns. Okay, so this is going to be M starting from its first row, second row, all the way to row R, first column, second column, all the way to row C. And what I'm going to do is I'm going to expand this matrix and generate a new matrix that has 2 more rows and 2 more columns, just to avoid indexing problems. Okay. It makes coding easier to pad this matrix with 1 row at the top, 1 row at the bottom, 1 row on the left, and 1 row. So 1 column on the left, 1 column on the right. But you can certainly solve it without doing that. So let me just do that. This is going to be my new matrix, and I'm going to call it as new M. And I want to use indices that will relate both of these matrices together. So new M, this is the first row, second row. This is going to be R plus first row, R plus second row. First column, second column, C plus first column, C plus second column. Okay. So I'll take my original matrix M, right? And I'm going to make copies of it. I'm going to move it around. I'm effectively moving the ends in each cell, but I'm doing it at once for all the cells in the table. Right? So if you take this matrix and imagine moving it over here, right? So that means all the ends move. Actually, you shouldn't move it there because that's a diagonal move. You want to move it over here. Right? So that means all the ends moved up. And then we're going to take those numbers, which is going to be 1/4 of the numbers in n, and we're going to copy it into the new n. And we are going to repeat this process by moving it to left and copying the values into new n. Then moving it down, moving it right. Every time you are going to copy the values of m into new m. And now the challenge is to figure out those indices. So let me do it for the first one, where you are trying to move this matrix M up and copy it into new M. And initially, we'll initialize new M to be 0, right? That way, you start from 0, and then you will keep adding to it as you move this smaller matrix around. So we'll say new M. We want to refer to the first row all the way to R row. 1 all the way to R. And we start from its second column all the way to C plus first column. Comma, second column all the way to C plus first column. So that's those are the cells of the table with the reference frame of using the new M indices. Make sense? All right, so that's the sub table from new M. And then we're going to say equals whatever values we have currently, and they'll be just zeros, but I'm just going to repeat it. That way I will do the same operation for all the movements. Whatever is currently in there, plus M divided by 4. So that divides M by 4. You take a corner of N's, and those are all the N's that move up. All right? That's the first move. Let's move. Let's make another move. We're going to move to the left. So now we're going to look at this region. Thank you. So that will be new M. Oh, yes. It needs to come all the way over here. Running out of colors. So we'll say new M, second row, all the way to R plus first row, comma, first column, all the way to column C. And then equals, same thing, whatever is in that currently, to R plus 1, all in 1, comma, 1 colon C plus M divided by 4. So we took quarter of the N and moved them to the left. And you'll repeat these statements 2 more times to move them to the right and down. And you'll have the answer for just one iteration. And the question asks you to iterate this 3 times. So you'll have a for loop. You're just going to keep repeating this. Let me look at the MATLAB code for this. All right, so if t is not given, we're going to set it to be 1. Now, for convenience, we'll just store R and C equal the size of matrix M. We create the new matrix, new M, to be a matrix where you have 2 additional rows and 2 additional columns. And then we move M around and copy it into the region of new M. And you do that 4 times for each direction. Once we do that, then we shrink new M. We get rid of those additional rows and columns. So those are the ends that move off the board. Okay, so we'll just ignore them. If you were asked to keep those ends such that no end moves off the board, then you would take those additional rows and columns and add them back into the original matrix. But this problem is easier. You just select the inner matrix from the new M. Second to R plus first row, second to U plus first column. And you take new M and store it into M so that in the next iteration, you are using the new values of the board. All right? You should, uh, depending on how far you came. If you just copy it from the one-dimensional case and just change the number 2 to 4, that doesn't give you much confidence. But if you however, you get confidence. All right, so yes, this not yet, but it will be posted. Okay. Yes, and this lecture is also being recorded, and the recorded lecture will also be available. All right. So do you want me to solve it a different way or not? Most of you solve this using formulas, right? Which actually easier to think about, but this is just it's less coding. Okay, let's solve the same problem using formulas. We still need a matrix called new m, but now let's make it the same size as n. We're going to go over each row. R equals 1 to capital R. To go home. C equals 1. G. All right. I know I thought that. Okay, so we're going to go over the matrix and look at each cell. And for those cells, we're going to move the end up, down, left, right. But now we have to say if we are in the first row. Okay. And then we have to make sure that we don't move end up. All right. And you also have to check if you're in the first column. And if so, you need to make sure that you're not moving those ends to the left because you'll be indexing the 0th column. Not okay. To avoid that problem again is you could use the same idea. Create a matrix new m that has 2 additional rows, 2 additional columns, and now you don't have to do anything. Right? So let me do it with the text and without. So if r is equal to 1, if c equals to 1, then we don't really do anything. No, we will move, we can't move left, we can't move up. Um, we need to figure out where these ends will go to. These ends can go to right or down. If you're getting too complicated to think about it. So one way to solve this one is to look at it from the reference of the ends that are moving. The other way is to think about in terms of the new location that the ends move to. Okay. Let's do it that way. If we are in the top left corner, we have we can move from the right of that cell. So that's RC plus 1 divided by 4. And ends can come from the bottom, new and RC, and we have to keep doing this thing. Plus, plus M R plus 1 comma C. Right. So this is the top left corner of the matrix. Else if R equals 1 and C equals capital C, this is the top right corner of the matrix. copy and paste this. And the only ends that will come from here are the ones that come from left and from down. The first if statement looked at this cell and it added the ends that come from the right and the ends that come from the bottom. And the second if statement looks at the top right corner. Those will be the ends that go right or come from the bottom. Okay? All right. In the next step, we are just going to look at all the special cases and then do the middle part of the matrix black. So if R equals capital R and C equals 1, that's the bottom left corner. We could come from right, or we could come down from the top. Finally, if we are in the bottom right corner, then we can come from left, or we can come from top. Okay? If none of those corners conditions are present, then we need to check if we are in the first row. And now there are three places we can come from, right? So for any element that are not in the corner in the first row, look at this cell, you can come down this way, you can go, come from the left, come from the right, come from the bottom. So now you'll have three places to come from. Okay? So you get the idea, right? You'll repeat this for all the corners, all the boundaries, and then once you are in the middle of the cell, that's going to be, let's say, the else part, then you're going to have 4 different places to come from. All right, and that will solve the problem. I'm going to show some variation there. Okay. All right, so this is one way of doing it, right? But it's really long. And it doesn't, and it also has some problems. And one problem is if your matrix has just one row, then you'll not get that problem. If your matrix has just one column, your code you get some errors. It's convenient to think about the rows and columns separately. Okay, so we'll just consider if we are in the first row, in the last row, or anywhere else. And we will move. We'll only look at the move ends that can move up or down. So if R equals 1, then we can only come from the bottom for those rows. Mu M RC equals mu M R comma C plus M R plus 1C divided by 4. I might have forgotten to divide by 4 in the previous one. Okay. All right. Else if R equals capital R, then we'll come from the top. Else will come both from the top and from the bottom. Okay. And there's an additional if statement where we have just one row and we will just ignore, we'll just not do anything if it's the case. Okay? So if you have just one row, all the ends are going to go off to the top and down off the board. There's really no effective movement if your matrix has just one row. And we'll repeat the same thing for column. If our matrix has just one column, there's no movement on the columns that will result in ends on the new board because one column means the ends go off the board. And for the first column, the ends could come from the right. For the last column, the ends could come from the left. And all other cases, they could come either way. Okay? Make sense? All right. Now I'm going to modify this around a little bit. Instead of looking at individual cells, I can actually look at an entire row. So I'm going to move this, take this out of the inner for loop. I'm going to move it here. If I have a single row, I don't do anything. If I'm on the first row, I don't really need to know what column I'm on, right? I'll do the same thing for all columns. Make sense? All the other operations will also be the same. Similarly, this will end the for loop. Now I'm looking at the column for loop. And I don't need to know which row I'm on. I'll do the same operation for all elements on a row. All right, so let me cross my fingers and test the code. Four ends in the middle of this board, and they go up, down, left, right. Okay, so it looks like it's working. Let me show you graphically what I did. So I had my table, and then I looked at the first row, and for the first row, only ends, as far as rows are concerned, they can come from the bottom. Right? That was the first if statement that I looked at. If I'm in the last row, that was the second if statement, then these are the ends that are going to move into that. So that's why I added that entire row into the last row of the new matrix. And anywhere in the middle of ends should come from the top or from the bottom. That was the last case I considered here. Okay. So that sort of covers all the cases and use the same thing for all. Any questions? All right. Let me take this back. Let me just rename this to the Which solution do you like better? The first one or the for loop one? The for loop one? For loop who likes the for loop solution better? Who likes the matrix solution better? Yeah.